We'll start this new session with Clémend, who is going to present us an implementation in Ramses of two-coupled Poisson equation. So I will give you a warning 3 minutes before the end of your talk.
Yeah, it shouldn't be too long. Okay, so hello everybody. Welcome to my talk. I will tell you about this little project I did with my collaborator. You can see here. I think Johan should still be around, right? And yes, so I will present it a bit on the, say, formal way, because we developed, maybe I'm not the first one to do that, but at least I'd like to share it with you. We double all the Ramses routine on the gravity side. So, well, judging for the previous talk, I fear at least the physical application will be a bit different, because we are more on, say, the large cosmological side. But okay, hopefully we can still talk together, right? Yes, so okay, the headline, the outline of my talk is the following. I will first, show you a bit on the formal way what I tried to do. So yeah, I doubled all the Ramses on the gravity side routine, so the gravitational potential, and I assume there is two species, matter species. So I use this tag implemented in Ramses, and I try to look at the equation I wrote down, 1 and 2, with F1 and F2 remain to be what you would like to put. So, okay, you have to choose some specific example. So hopefully, if you know some other, I'm happy to apply my patch to some, gravitational setting. But, in the general case, I guess it's possible to do that. I'm also happy if you tell me something about this conjugate gradient method, which is inside Ramses. And in practice, because in practice, I guess you can take anything you want for F1 and F2, but maybe there are some pathological case. So if somebody knows something about that, I'm happy. And so this is a general case, and then I apply it together with Professor Chardin and the other to this Dirac-Min cosmology, where in that case, F1 and F2 are given by what I wrote down. And for the rest of this talk, I will call it this one matter and this two antimatter. Good. Okay, so in one slide, what I mean by Dirac-Min cosmology is a say rebel or other way to look at the cosmological observable today. So it's a program of research which is a small. We are a small group, so be indulgent with us. It's a try, to go beyond. Not beyond, but to reinterpret everything, it's not, you don't have a continuous limit to lambda CDM cosmological model. And it's a try to say, look, we've been too far. We don't believe anymore this dark energy, dark matter. We should stop. And we try to build something else from scratch. So it's super ambitious. And obviously, it's not as advanced as the lambda CDM model. Otherwise, it would be the standard model of cosmology. But I guess it's okay, to let people try and to see if something can go out of this. So, okay, so the bottom line is try to say, look, dark matter and dark energy, it's too much. Obviously, there are overwhelming evidence for them. I'm not fighting against that, but why not trying something else and see where we go? So in that case, as I mentioned before, you end up with the equations 3 and 4. Where you have the two matter and antimatter species which gravitate in some strange way. And you see, compared to usual Poisson equation, you see my mouse, right? I guess yes. I assume yes.
Yes.
Okay. You see there was a bunch of minus sign here. And in the Poisson equation, it means that actually somewhat you have anti-gravitation. So you have a negative contribution in the Poisson equation. And somewhat this is a bit what is doing the trick of not having dark energy and those sort of things. So it's also exotic, as I would argue. Also, dark energy is somewhat exotic to Earth-link physicists. And you can put that in Ramses and try to see what happened. So just to give a bit more overview, I will move back to Ramses and so on. But you also assume that you have as much species 1 and species 2, matter and antimatter. And this helps you to solve this whole problem called the, asymmetry, matter and antimatter asymmetry problem. So, the early universe equations are symmetric between matter and antimatter, and we don't know why today we see only the matter and we don't see the antimatter. So the idea is that the antimatter is hidden far away from the matter because it repels. So it helps to solve some problems that are worrying particle physicists. And since antimatter, the second species, antigravitate on the larger scale, you have you have as much matter and antimatter, but the antimatter contribute with opposite sign. So on the larger scale, it looks like an empty universe. So, void. And therefore, you have this mean cosmology, which describes the sort of universe. But in that case, the expansion is only coordinate expansion. So, okay, those are mainly the main feature of this cosmological model, which, maybe is worth investigating, at least see what it gives when you put into Ramses. So I put you some references here. So it's mainly Professor Gabriel Chardin with his collaborator. So he's PhD student in IAP, Aurélien Benoît Lévy, who look a bit at nucleosynthesis, CMB, supernovae. And more recently, he looked with Professor Manfredi in Strasbourg with a one dimension and body code at structure formation. Okay, so yeah, what I did was to put that into Ramses. That was my job. Good. So the scenario in this cosmology, first point is that since you want to have matter and antimatter after the CMB, you are directly in the non-linear regime. And since you don't want them to, annihilate really quickly, you want to make them disjoint at the early time. So we start from some quasi-homogeneous but disjoint patch for matter and antimatter. And you want to start as soon as the end of recombination. And you let it go. And, just with physically the intuition, what happened is that the standard matter, when it sees just matter around it, it will collapse into some structures, a galaxy and so on. Whereas the antimatter, this new exotic, strange component, which don't obey gravity the standard way, since it repels, it anti-gravitate, it will just spread wherever it can go. So that's what you see in Ramses. And then the typical structure you would see is the picture I put for you here. Is okay, a collapse matter, a galaxy and something, and everywhere around spread antimatter, but also you have to remember that antimatter and matter, they do repel also each other. Therefore, you have some zone where you have nothing, at least in the n-body simulation, it's totally empty, and it's a buffer zone, depletion. Okay, so that's the typical thing you would expect to see if you just think, naively. And now I want to show you a more, so this is an ideal, say, galaxy, that you would expect to see. And now we want to have a lot of those galaxies. So I want to show you, so that's what we run, the simulation. So I wrote for you here the numerical setup. I want to add that we put periodic boundary condition. That's necessary. It's hard to simulate isolated galaxy because, as you understand, the second species, the antimatter, it goes wherever it can go, So if you don't put a periodic boundary, it will just go out of the box, So yeah, so that's what we did. Hopefully, I can show you a movie also that Johan made. So I will give it a try. You let me know if your laptop explodes. Okay, do you see something?
Yes, we see something.
Super. Okay, let me play. So, okay, we start, as I told you, from homogeneous patch, almost with two disjoint species. And okay, the blue is the matter and the red is the antimatter. And you see that, okay, more or less, as I told you, you start to form some sort of structure. The blue, they collapse. The red, it goes wherever it can. And in the black, you see that there are some zones where you have no particle at all. Okay. So, okay, that's more or less, okay, if you had enough, I can show you one more time. But that's more or less what we run. So it's some humble simulation. Okay, we are not at the level of Illustris or whatever. It mainly simulates, okay, what we hope to be some small galaxies. And okay, this is more, okay, visualization. And I try to tell you a nice story about that. Let me try to show you a bit more quantitative results. If I can switch back to my presentation. How do I do that? Yes, I guess you see again. I hope you see again.
Yes.
Yes. I wanted to tell you that so far, what I've been showing you is assuming that the matter that hopefully is not dark matter. So let me be clear about that. We assume it's in the particle sector of Ramses for the moment. I also did for Hydro, but didn't publish it yet. But okay, the results are kind of the same, at least so far. What I show you, it's all also for the Hydro side of Ramses. But you know, as usual, you start with simple problem. You assume that okay, this matter is collisionless and so on, and then you construct upon that. Good. Do I want to tell you something else? Well, let's move on. Okay, so I was telling you some more quantitative results. So we run some halo finder on that. We find the halo. And we try to look at some characteristics. In particular, we look at this Tully-Fisher relation, the scaling relation, the mass of the halo as a function of the velocity dispersion, the asymptotic. And we found some typical scaling relation. So as far as I understood, with this Tully-Fisher relation, the more important is that you have a tight scaling relation. You know, it's the blue dot are not spread out in the whole box.
You have 3 minutes left.
Okay, but it's good. I'm almost done. Yeah, so a part of the community is worried about the slope of this scaling relation. So with our first run of n-body simulation, we found a slope, let's say, closer from 3 than from 4. And you may know that there are those people from the Monde community who argue it's more 4, I think, whereas the so-called lambda CDM people are more advocate of 3. Okay, there are some debate in the community about that. I don't want to go too much into the detail, but at least we have some prediction also. Let me try to show you also this. So if you define those two fields, GM and G+, so the GM is you see that I take the difference between phi1 and phi2, and if you go back to the Poisson equation, it will be created by matter. So rho 1 will be the only one contributing. The matter will only contribute to GM. Rho 2 will simplify, because you just make a subtraction. In the case of G+, it's just the gradient of phi 1. So in that case, it's phi 1, it's what phi 1 is doing. And the people, at least in Monde, are looking at those sort of things. And so this is a density plot. So the colors are representing, all the dots in my simulation. I measure that in the n-body simulation. So in, standard gravity, normal, both are equal because phi2 is 0. And you see that there is a typical scale, typical acceleration, typical gravitational force, where, this modification of gravity breaks down. And it turns out it's close from the typical Monde acceleration that you may know is 10 to minus 10, 1.2 10 to minus 10. So it makes us think that somewhat this might be related to a typical thing like Monde is also seeing. And but it's not the same, huh? But so our guess, and this runs to my conclusion. Yeah, okay, so yeah, our guess is that it's time dependent in our case because this was not at redshift 0. But let me wrap this up. So, okay, we are humble group, 4 people working on that. So, and we found that, we have some sort of phenomenology on galactic scale. So the other galaxy, for instance, what Johan was showing and so on, we are not as evolved. We are not simulating galaxy as with such a very nice program of research, but we are starting, obviously with the simplest thing. And we see that there are some room to do something at least. That's all we say. So I started to do that for baryon, because I told you there is no dark matter in this model, so I should do it for baryon. So I did with a fluid. And obviously, if you want to do something, you know, state of the art, you need to add some sort of feedback. So I'm starting to do those things. And yeah, and then maybe we can try to do some more serious rotation curve fitting or look at the data, which is not, we are not in position to do that yet. As I told you, as we understand the acceleration scale, this almost 10 to minus 10 would be within the n-body simulation I run time dependent. So this might be a prediction. Okay, we are not the only one to think about that, but one would need higher redshift rotation curve. Most of the Spark rotation curve and so on are at redshift 0. So that's a prediction. You know, if in the future we can see something like that, would be also, you know, compatible with this model. One thing we are a bit annoyed about or worried is that you know, usually when you go to the larger scale, it's easier to run an n-body simulation because we are in the linear regime, so it goes fast. But since we started nonlinear all the way from redshift 1000, you know, it's harder to run on a large dynamical range because you need a lot of computational power that at least I don't have yet. And you want to have some decent resolution because from a theoretical prediction of this model, you need to resolve, you know, co-moving kiloparsec scales all the way from redshift 1000. So, you know, it's a complicated problem to run it all the way to, say, gigaparsec scale, to measure a power spectrum, to do all those cosmological probes. That's why we stay to galaxy so far. Yes, what one can directly see since you start non-linearly and so on in the structure formation is that you form more structure because you start to form all the way from redshift 1000. So hopefully this can be also, you know, a clear prediction to rule out or infer this model. And finally, okay, the biggest assumption, the thing everybody is crying is that, you know, antimatter antigravitate, and you have some people, particle physicists, looking in CERN on that. So all of this model, you know, is more futuristic in the sense that those experiments are, I think, running now. I didn't check the latest, but, you know, should be running in the next year for sure. They have some results. So, okay, if they claim a huge surprise, everybody will fall from their chair. Then maybe this model would be worth to spend more time investigating. Otherwise, if they claim everything the whole community is believing, antimatter gravitates, as every quantum field theory people would say, then maybe this model, you know, is not that worth investigating. Okay, and yeah, I'm okay to take question and also ask you questions. So if you have another idea, easy one to implement to reuse my patch, I'm more than happy to chat about them. Good. I stop.
Thank you. So we have one question from Patrick first.
Thank you. I think it's interesting to keep diversity and explorations of various things. Something I didn't understand is, so, I mean, in standard gravity, you need the dark matter to form your galaxy, I mean, fast enough. And with MUND, this is the extra gravity which is playing this role. I didn't understand with the repulsive gravity, how come that the galaxy would still form fast enough as explained? Why is the gravity faster than the baryon, than the purely baryonic gravity?
Yes, so you do have somewhat a new force that is due to the cloud. So let me maybe show the picture so that it's easy. So this cloud here, you still see my mouse, I guess. This cloud here, it makes a new force, you know, all together, you know, you ignore this and you calculate, you know, the new force created by this cloud, and this cloud creates a new force. And this is hopefully, you know, so this is the physical mechanism. This is a new thing.
But
which hopefully,
sorry, but this cloud, if I understand, is antimatter.
Yes.
And so the repulsive antimatter so because antimatter is repulsive, but
yes,
still,
yes, it has negative mass.
Still it kind of creates an extra gravity sort of.
Exactly, and the extra gravity, you can see it here, for instance, this yellow. I don't know, was it clear enough, this plot?
No, but what I don't know whether it's clear for others, but it's not clear for me. How do you turn a repulsive force in something which operates as an effective dark matter, which accelerates the gravity of the baryons. This I don't catch.
Yes, okay. Let's put it this way. You ignore this dot at the center, and you fill this empty circle with also antimatter. Then you have no force, huh? Because it's a homogeneous box, you know, nobody is feeling nothing. Therefore, if you take away now, and then you apply superposition theorem, you know, from Gauss electromagnetism, or, you know, therefore, if you take away the circle, you would have a net force which would push. Does that make sense? Or
yes, okay, yeah, okay, thank you.
Okay, thank you. Unfortunately, we don't have time for more questions. I'm sorry for Jan who had a question. Maybe you can continue the discussion on Slack because we should move to the next talk. So, Tine, if you can share your slides. Thanks. So now we will have Tine who is going to talk about the Great Merge, progress towards unified Ramses.
Yes, I should unmute myself first and then share the screen. That will work better. Let's see. So I wanted to take this opportunity to talk a little bit about some effort we've been putting into with the people in Saclay and Benoît Commerçant also, to merge all the features we've developed in different versions of the code, to merge it back together in one central repository. So there's many different Ramses users, and as a result, we have all our own version with our own physics modules. And this can create some issues. An important one is that bug fixes are not always applied in every version. So I've seen this both ways, that something was fixed in the main repository, not pushed to another version, or the other way around. Also, often work is duplicated because people are not aware of what other people are already implemented or what they are currently doing. And it complicates sometimes the comparison of results. So that's why one of the reasons we want to merge back into one central repository. So this has many advantages. You have this overview of what everybody is doing. You have more physics available to use in your own simulations and to play with. You can also have, if you implemented a new feature or physics module, you can have your code reviewed by a lot more users, which in the end results in less bugs and easier maintenance overall. So we'll talk here a little bit about the case of Ramses ISM, since right now I'm at CE in Saclay. We use the Ramses ISM version for star formation simulations. So you can see it's a fork of Ramses, which is a lot of commits behind. The master branch has been last updated in 2017, but there is still a lot of active development on this main Ramses ISM branch. So the issue here is that you cannot do a simple merge back into the main repository because both have diverged too much. So instead, we are trying to do a different strategy, which is first to identify all the physics features that have been developed. So there are a lot of big ones, for example, non-ideal MHD, dust, turbulence driving, radiative transfer using flux-limited diffusion, several modes of stellar feedback, ISM cooling, and cosmic ray anisotropic diffusion. There are several smaller ones, but I will not mention them here. So the idea is to isolate each of these features individually, clean it up a little bit, because often you use this code and there's a lot of stuff commented out, which you use for testing, which is not useful anymore. So we clean up the feature, make sure it fits nicely into Ramses, push this update. Once it's accepted, we synchronize the feature, the the changes back to Ramses ISM, so you have the same version of the feature in both versions of Ramses. We do this for all the features, so in the end, you'll have something which is much more easy to synchronize, and we can get back to having one code. So for each feature, it sort of works as the procedure we are applying works as follows. We have Ramses ISM here on the left and Ramses on the right. And in the middle, we have kind of a Ramses development fork, which I keep in sync with the latest Ramses version. So first we isolate the feature code, implement it as it is, and then design or write some new tests if they are not already available in Ramses ISM. And these tests are very important because we want to run them on both versions of the code and make sure they give exactly the same results. So we can make sure our implementation in the other version of Ramses is working fine. Once we have validated this step, we can move forward and clean up and refactor the code to comply to certain guidelines. First of all, features should be as isolated as possible and able to switch it off and on. You should have separate files for feature routines and variable declarations. This will make it a lot more easier to maintain the code. Of course, minimize code duplication, and each feature should have the documentation and tests associated with it. And of course, you want to ensure input and output backwards compatibility. So once we are happy with our version, we submit a pull request to Ramses. This is then reviewed by several people, and this is an important step because you want to make sure the code is like cleaned up properly. There's not any mistakes that have been made, something removed that should not have been removed, for example. Once this is passed, the pull request is accepted, and we synchronize the changes back to Ramses ISM. Of course, you should not forget documentation. So in minimal, this is a list of nameless parameters with the description of what each parameter is doing. So because if you don't have this, people will not be able to use your model, because if you're a beginner user, you just don't dive into the code to see what all the variables are doing. So an example, which has been already ported, is the turbulence driving module. So this adds forcing to the box to generate or maintain turbulence. It was originally developed in 2014 by Andrew McLeod, who's now left academia. So it was like, if I had questions, I could not really contact him, which sometimes was a bit annoying. But the good thing was that it was pretty much already a standalone module. It was nicely defined in the code. So it was fairly straightforward to move it to Ramses. The only annoying thing was that it has a dependency of FFTW3, so an external library, which it uses for Fourier transformations. The implementation is basically this. You have this, I won't go into the details, but it makes use of this generalized Ornstein-Uhlenbeck process, of which the force has this component which has a random growth and decay with this time t. So as you can see, the code was nicely isolated with its preprocessor directives. So I ported it, and as you can see, there are already minimal changes to existing files. And we have this new directory called turb, where we add all of the stuff related to the turbulence module. I just added this README to explain how to install FFTW3 if it's not available on your system. So in the make file, you can choose whether or not to compile with turbulence, and you can change the path to FFTW3 here in this location. So we have this new nameless parameters. We have this new name list to describe the turbulence parameters. You can turn it off and on. For example, you have here, you can set a fraction of compressive modes versus solenoidal modes. You can alter the strength here, choose the autocorrelation time here. And all these are described on the Ramses wiki in a little more detail. So I added this task case, which was important to check if the implementation is working correctly in both versions, which is just a uniform box where you add some driving and then you generate this nice, nice looking turbulence. So this is then the final pull request. Not much has changed compared to the previous diff I showed. The only difference is here this synchro hydrofine. So basically, this turbulence force acts as an external force in the earlier equation in a way which is almost exactly the same as gravity. So it's possible to reuse the routine for gravity instead of having a duplication for turbulence. So that's what I did, and I cleaned up this duplication in the MHD file. So in the end, we have an easier maintainable code. So you can check out the pull request here. It's now available in the main Ramses ISM. So there are still some small developments that are ongoing. I'm adding some more options to select modes, which is useful if you want to drive, for example, only on scales, which are half the size of the box or 1/3 the size of the box. And then I'm also writing a more extensive user guide with the description of the implementation and a bit of a guide on what parameters to choose, because it's not straightforward. For example, if you want to obtain let's say an isothermal turbulent box with a certain Mach number, it's not so straightforward to know what driving strength you need to use to obtain this, this Mach number. So
you have 3 minutes left.
Okay, thanks. So this is an overview of what is still left to do, what is currently in progress, and what has been done. So I'm currently working on, so currently Patrick Kennebel and Noé Brissy are working on the coupling of the ISM cooling and coupling it to the H2 formation, which is already in Ramses ISM, and porting the feedback from sync particles. I'm working mainly on finishing the merge with non-ideal MHD, which I hope is almost done. So I have ambipolar, it seems that ambipolar diffusion and ohmic dissipation are working, but the Hall effect is still a little bit broken. So I need to figure out what's going on there. And then apart from the turbulence method, turbulence driving module, we also, that's mainly Corentin who did most of the work here, reported his Monte Carlo tracer particles. So now everybody can use tracer particles, which is awesome. So you have the details of the implementation in this paper. You have this very simple name list. So an example here. So I just a uniform box with turbulence, which I used the turbulence driving method described before. And I in place, so this is the in place thingy here, generate some initial tracer particles, and then you can see they follow the turbulent flow basically. If you add more tracer particles per cell, your description is obviously better. And then the last thing is that we added a little bit of more easier way to have analytic equation of state. So I replaced the isothermal keyword with what it actually does, which is barotropic equation of state. You can still use this one, it's fully backwards compatible. Now you can easily choose a barotropic equation of state from, for example, isothermal, and set the temperature of your isothermal thing here. So now, how can you help to push this effort forward? First of all, use Git branches instead of patches for development. I know that some of you are still doing this. It's very difficult to maintain the code like this because you don't have this, you often don't remember which commit you took the patch from initially. So merging it back is a lot of work. While if you just use a branch, you can merge automatically the patch, the changes that have been done in master into your branch to be keep updated with the latest developments. And once your feature is done, you want to publish it, you make it available for everybody, can just merge to the master branch. Another thing which would be very helpful is if you add your typical low resolution setup as a test case. So right now we have a very limited number of test cases in Ramses, and the more test cases I have, the easier it is to catch bugs with new developments. So if you don't know how to add a test case, you can just ask me, I will explain to you. It's very simple. If you haven't done it once, then you can do it many more times. It's really straightforward. You just have to know how to do it. And then, of course, I would encourage everybody to merge their physics features back into the main repository. And if you want help with this, you can join the Ramses merge Slack, or since Yoki is now reviving the Team Ramses Slack, we can move this effort to Team Ramses and just make channel-specific, feature-specific channels where we discuss the merge or the physics or the work that has to be done to merge your thing back into the main repository. So I'll just leave it here. That's it for today. Thank you for your attention.
Thank you. Thanks a lot for your talk. Do we have question or feedback from the audience? If yes, please raise your hand. Johan.
If you end up with having, well, first of all, that's a nice effort. But if you have two competing developments for the same routine, say the sync particle, for instance, how do you decide which one should stay or to merge them? Or if you really want to merge them, it will require a huge effort. Probably, but I mean,
the thing is, if you have both people who were doing the developments, it's much easier because they know which parts are critical for the physics they need, and then you can just arrange it so that you can switch between both implementations, for example, from the beginning. So it's I wouldn't. It depends if you're. How good your coding skills are, I think. But this is the kind of stuff I like to do to see how to actually match the two and make them both available. So it's not really a problem.
Any other questions or comments? Otherwise, we can move to the next talk. So, Taehwa, if you can share your slides, yes. So now we will move towards more reionization-related talks, and we'll start with Taehwa, who is going to talk about the clumping factor of the intergalactic medium at the epoch of reionization in the Sphinx simulation.
Thank you for introducing me. Hello, I'm Taehwa Yoo, student of Ramses University working at ThyssenKrupp. Today, I'm going to talk about the clumping factors of the IGM at the epoch of reionization in the Sphinx simulation. Many studies have worked on reionization by reconstructing the history of global ionization of hydrogen. And to do that, one needs to understand how many Lyman-contained photons can escape from galaxies and ionize the neutral hydrogen in the IGM. And this can be estimated from the galaxy luminosity function and their SED and escape fraction. And on the other hand, one needs to consider the recombination of hydrogen in the ionized region, because rapid recombination means the low net ionization rate. So the speed of recombination can be quantified as the recombination timescale, which is the inverse of the product of hydrogen density and recombination rate coefficient, and the clumping factor defined as this. For gas with a high clumping factor, it leads to short recombination timescale and low net ionization rate, delaying the reionization process. The reason why recombination timescale is a function of a conflict factor with a form of this is simply because a recombination rate is a function of the density square. So the conflict factor has a density square term in the numerator. One can easily understand the concept of clumping factor by some analogy. So when you want to air dry your clothes, it is better to stretch your clothes for faster dry. And the photonization of the IgM is like air dry of laundry. So when you have clumped clothes with many wrinkles without stretching it, it results to slow dry. And the clump clothes are like the gas with a high clumping factor, leading to slow photonization. Although fundamental physics behind this process are a little bit different, but this analogy is useful for you to remember how does the clumping factor works. Analytic realization models use this clumping factor to produce a neutral or ionized IgM fraction using this equation. Well, the QH2 means the volume fraction of ionized hydrogen in the universe, and the N dot ion is the total number of ionizing photons ejected into the IgM. And there's a cosmic average hydrogen density, and there's a recombination timescale term, including a clumping factor. Realization model often assumes no clumping of the IgM, meaning clumping factor of unity, or constant clumping factors, for example, equal to 3, or time evolving clumping factor obtained from numerical simulation. The commonly used one is the result from Poly 2009 that measured the clumping factors from hydrodynamical simulations with softening lengths 1 kiloparsec and uniform background radiation. Since the clumping factor used in these realization models are originated from the numerical studies, clumping factors are model dependent, and it is important to make a realistic IgM structure in the simulation. We decide to measure clumping factors from string simulation as it has a high spatial resolution. So it enables us to resolve small-scale structures in the IgM that might affect the clumping factor measurement. Also, a string simulation employs fully additive transfer calculation, so self-consistently remodeling the formation of ionizing bubbles and the photonization heating of the IgM. So those processes are important to estimate the clumping of the gas as well. When you measure clumping factor from simulation, we flag the gas cells in the simulations and obtain the average of the density for the flag cells. During this calculation, there are a couple of criteria for the flag. First, we need to distinguish the IgM from the gas inside the virial radius of halos, because we are only interested in the ionization of IgM in the era of realizations. And second, clumping factor should be measured inside the ionizing regions where the recombination actually occurs. Otherwise, the average recombination timescale can be overestimated by including gas cells in neutral void regions into the calculation. This is the result of giving different criteria for the flags in the measurement of clumping factor. Purple line indicates the result of including all the gas cells into the calculations. So it starts from extraordinary high value like 10 to the 9 and less 25 and decrease with time. This is because only a minority of volume is ionized at the early stage of realizations, leading highly inhomogeneous density distribution of ionized hydrogen in total, and become homogeneous as more volume is ionized and the clumping factor decrease. When you only account for the IgM, the green line does not reach that high value, as neutral and dense gas cells inside the halos are excluded, but they show some similar trends. The red line, which we are interested in, is the result of ionized IgM. it reflects the density distribution only inside the ionizing bubbles, and it is no longer affected by the volume fraction of ionized hydrogen in the box. Since we get a relatively homogeneous density distribution only inside ionizing bubbles, so we get pretty low clumping factors, like lower than 10. There was an issue that which ionized fraction threshold we should use to define ionized region for the clumping factor measurement. The strategy is that converting this clumping factor with different ionized fraction threshold into the volume filling ionized fraction QH2, and it can be compared with the actual QH2 from the simulations. So the clumping factor of which QH2 shows the closest match with the actual QH2, the blank line, would reflect the clumping factor of ionized region in this simulation. So the colored lines are the QH2 from this clumping factor with different ionized fraction threshold, and we can compare their offset with blank lines in each other's, and we can find some minimum offsets. And the clumping factor showing the minimum offset is 0.9. So our best shot is the clumping factor of the gas cells of which ionized fractions is larger than 0.9. Our best shot is compared with previously introduced clumping factors from FOLIC 2009, the blend line, that have been commonly used. After fitting clumping factors, we can reproduce the volume filling neutral fractions and the Thomson optical depth from this clumping factor. And it shows almost a similar result with the FOLIC 2009, even though our measurement is slightly different from FOLIC 2009 data. So far, I'm talking about the clumping factor measured from whole IgM. But now we are moving to the clumping factors measured locally around halos. This can be useful to model local ionization history in semi-numeric tools such as 21 centimeter FAST. It basically has a large grid about some kiloparsec scale, and the ionized fraction of hydrogen in the grid can be measured by comparing ionizing emissivity and the recombination rate within the grid. There is a clumping factor term in the recombination rate. And the thing is that this can be different from the clumping factor measured from the whole IgM. So clumping factor should be measured locally for this kind of work. The method of local clumping measurement is simple. So for each halos containing galaxies, we measure clumping factors in the regions between the virial radii and some specific radii outside the virial radii. And we apply ionized fraction threshold to capture only ionized cells. We look at the correlation between halo mass and local clumping factor. We set R is equal to 1 kiloparsec. Each point indicate the measurement of local clumping factor for each halo. And I connect the median values from each bin with magenta line. And you can see some positive correlation between halo mass and local clumping factor with some large scatter at all redshift. The correlation become stronger when I plot stellar mass versus local clumping factors. So one needs to consider that the recombination rates around halos are not uniform, but it depends on a halo mass or stellar mass. I'm currently looking at why massive galaxies or halos have high clumping factors. And I will give you some examples of projected image in the local regions around halos. And first, in low mass regimes, many halos have low clumping factor. And this is the example of the one halos in this regime. From left bottom panel, on the cyan circle is the virial radius, and the magenta one is some specific radius outside the virial radius. I exclude the gas cells inside the halos in this image, or the image, so you can see some empty hole in the image. And we basically measure clumping factors from the region enclosed by this magenta circle. So the left one is the baryon density and ionized hydrogen density. In the right, at the top panel, since we are only captured ionized cells in the calculations, I plot the projection of baryon density in the ionized regions. And the rightmost one is the ionized fraction of the hydrogen. The common characteristic of this halo in low mass region with low clumping factor is that the gas cells around them are almost neutral. You can see they are all blue, meaning that their ionized fraction is lower than 0.5.
Taehwa, you have about 3 minutes left.
Oh, thank you. So only a minority of gas cells are flagged for the calculations. So you can basically identify some structures along in total NH projected image, but you cannot see those structures in this image that's showing only the ionized regions. So the common characteristic of these halos that their ionized bubble is not formed yet, that leads to the low clumping factor. But some low mass halos have high clumping factors. Their environment is partially ionized. You can see some green regions that is ionized along the halos. As more gas cells are ionized, we can include more gas cells into the calculations. So the density structure inside the ionized region becomes more complex. This leads to high clumping factors. This situation is common for massive galaxies or halos. They already develop the ionizing bubbles around them. So the low density region is ionized, while the filamental structures remains neutrals. So that's why there is no low clumping factor in the high mass regimes. Some massive halos with high clumping factors have some cavity around them. So there are some low dense regions and high density regions all together that maximize the local clumping factor. So the final aim of doing this is we want to constrain these local clumping factors. For a given stellar mass, there is still huge scatter. So it is better to make a narrow and strong correlation. And it seems that more than a couple of factors affect local clumping factor. I'm suspecting that not only baryon density structure, but also the presence or size of ionizing bubbles might be important to determine local clumping factors. So I'll look at the correlation with additional pointer space to better constrain the clumping factor. That can be very useful to modeling the subgrid ionization history. So this is the conclusion. So when you only consider for the ionizing regions, we found that the clumping factor of IgM slightly increased from clumping factor is 2 at raised to 15 to 6 at raised to 6. And it can reproduce similar observables like Thomson optical depths with previous estimation from 2009. And we also measure the local clumping factors, and there's some positive correlation between the clumping factors and halo or stellar mass, which is useful information for subgrid calculation of local ionization history. So this is the end of slide. Thank you for listening.
Thank you, Taehwa. So we have one question from Luke first.
Hi, yeah, thanks for the nice talk. I just wanted to ask, when you talk about extracting the IgM, so cutting out your halos, how do you handle gas cells that are sort of half in the halo and half out of the halo? Do you only take cells that are totally outside the virial radius, or do you take some average of the cells? What do you do?
So I I only include the gas cells outside the virial radius of all the halos.
Okay, so only if they're totally outside that you use them.
Yes.
Okay.
Yes.
All right, thanks.
Yes.
And then Hale.
Hi, Taehwa, really nice talk.
Yeah, hi.
I have a question on your first conclusion where you said you need to consider only cells with an ionized fraction greater than 90%. So where you showed the plot where you compared all the different values, one of the things that I guess I had a question about was the recombination rate is also temperature dependent. So what temperature did you use? And if you varied that, for example, plus or minus a factor of 2, would that first conclusion change?
Yes, that's very good questions. Actually, this clumping factor of CH2 considers constant temperature like 20,000 kelvins. So the recombination rate coefficient is assumed to be constant. But when I compare this with the actual QH2, I consider the different temperatures of the gas cells. So I consider different. So the clumping, in that case, the clumping definition of clumping factors and recombination timescale would be slightly changed. So yeah, so I want to say that I consider the different temperature of the IgM for this comparison.
I think what I was saying is maybe it's on the previous slide.
This one?
No, it's okay. Why don't we can chat afterwards? I don't know exactly which slide it's on.
Yes, okay.
Okay, thanks. We can take Maxime's question.
Thanks. I hope you can hear me.
Okay.
Thanks, Taehwa, a lot for the talk. That was super interesting for me, at least. I'm just wondering, the Sphinx simulation is, because it has such a high resolution, it is limited to a fairly small volume, even if like 20 megaparsec now for like the bigger one is amazing for this kind of work. But isn't there a risk that this is still too small to have a good handle on the clamping factor of the IgM as a whole?
Yeah, that's very good questions. I will explore. So this is the result of the Sphinx 10 with 10 megaparsec size, and I'm now testing that this result of clumping factors is dependent on the box size. So I look at how this value is changed with the box size and see this value is converged or not. So it will tell that this box is enough for the calculation of the clumping factors.
Okay, I guess my only worry is if you start to have a volume that's large enough to have deeper voids and larger overdensities, because you have this n squared term in the clamping factor, how is that going to affect the overall thing? But I'm very looking forward to the result on larger volumes.
Okay, yeah, thank
you. Luke, your hand is still raised. Do you have another question or?
No, sorry, I'll take it.
Okay, so Jeremy, would you like to ask something?
Yeah, sorry, very naive question. Thank you for the very nice talk. I was a bit confused why you decided that 0.9 as a threshold for selecting the ionized regions was a good threshold. I sort of expected that you want your measurement to converge to the measurement where you have no threshold when the volume is completely ionized, and this doesn't seem to be your choice. But I just misunderstand something.
Sorry, could you repeat the question? So
yes,
I didn't hear your yeah.
My impression was that when the universe is completely ionized, you should not use any selection on the region. You want the global recombination rate, right? So why do you select a threshold for ionized regions, which does not give the same value when at the end of the simulation?
I think this is. I think even if the realization is over after H27s, there's still neutral regions around in the box. I think so. They are not perfectly ionized, and some gases are not just partially ionized. So I think that makes some difference, I think. And especially there are some dense gas cells very outside the halos. And it is hard to ionize those dense neutral regions even after the 7. So depending on the ionized fraction threshold, it can change the clumping factor values. That's my speculation. Yeah.
Okay, thank you.
Thank you, Taehwa. We should move on with the last talk before the lunch. Pierre.
Yes. Let me share my screen. Yeah. Okay. Can you see this?
Thank you. So we'll have Pierre talking about Cosmic Dawn 3.
All right. Thank you very much. Okay. So good morning, everybody. The Cosmic Dawn 3 simulation project is an attempt at using the most powerful supercomputers in the world in order to understand reionization, how it works, how galaxies form during the epoch of reionization, how they drive reionization, and how then the changing IgM, because it's irradiated, in turn changes how galaxies form. And this coupling between galaxies driving reionization and then reionization changing galaxy formation in return is really at the core of this project. I'll do a quick introduction and I'll talk about some technical aspects of the simulation, and I leave most of the science to my former student Joe Lewis, who is speaking in the afternoon. So please don't miss his talk. So I'm speaking on behalf of a bunch of people who have collaborated to the project throughout its existence. So people helping with development, with optimization, with deployment, and with the analysis. Some of them are here. So reionization, in a nutshell, this is a time frame with time going to the right. Okay, Big Bang is here. After Big Bang, you have recombination. Then the first stars formed in the dark ages. They start reionizing the IgM. There's soon some sort of partial overlap between the H2 regions that these first stars produce, and then later on you have a stronger overlap between these H2 regions, and between redshift 6 and redshift 5, we don't know exactly when, the universe becomes completely reionized. What we're doing here in terms of simulation comes in support of a very strong observational development, okay, with the development of the upcoming and already in operation 21 centimeter observatories, radio observatories, and the imminent launch of new space telescopes such as JWST, Euclid, and things like that. So when you want to model reionization, you end up with a number of fundamental questions, okay, such as when did reionization start and finish? What are the ionizing sources responsible for that? What's the photon budget of the universe during the epoch of reionization? How does the escape fraction change with galaxy properties and with time? How strong is radiative feedback on these galaxies? And addressing all these questions numerically is very challenging. First, you need a coupled radiation hydrodynamics code, okay? There's more of them today, but some time ago, there wasn't so many of them. You need a relatively high mass resolution and also a rather large volume in order to sample the variety of environments that you can have, and fair enough, and to have a fair enough sampling of the galaxy population. Okay, so these are sort of the requirements of the Cosmic Dawn simulation suite. The code that we use is not in the main trunk. It has branched some while ago, and then I went back to it for the newer versions and then branched it again. Hopefully I would be able to merge it back together with the main trunk at some point. So in this code, Ramses takes care of most of what happens in terms of gravity and hydrodynamics on the CPU. Okay, but the GPU takes care of the radiative transfer using the Atom module written by Dominique Aubert. So that's a radiative transfer code which takes care of hydrogen ionization, photon propagation, photo heating, and cooling. Okay, so in one time step, Ramses sends the relevant field to Atom, okay, which runs and then sends back the relevant hydrodynamical values back to Ramses. Okay. So you may know that in this case, you spend a lot of time actually doing the radiative transfer because of the very strong Courant condition imposed by the very large speed of light. So here, what we're using is an optimization which allows Atom to run on the GPUs, which yields a very large speed up, allows us to use the real speed of light. And we think that's important in particular after reionization, so after overlap. But the very aggressive optimization which was done here to work with the GPUs forces us to run in unigrid and to not use the AMR features of Ramses. Okay. All right, so we need lots of GPUs. So we used to run on Titan at Oak Ridge National Laboratory, so that's in the US. This is a very big machine, has more than 80,000 GPUs. So on this, we performed Cosmic Dawn 1, 2, and the Cosmic Dawn 1 AMR, which was done with Emma. Titan has been replaced with a newer machine called Summit, which I'm going to talk about very soon. So here is a quick summary of what this simulation has allowed, Cosmic Dawn 2 and in particular. So it's allowed us to do interesting things about the luminosity function of galaxies during the epoch of reionization, radiative suppression, look at how reionization happens at the galaxy progenitor scale and at the scale of local group as well, or pairs of galaxies. It allowed us to have a look at the photon budget of galaxies in the epoch of reionization. That's the paper by Joe Lewis. And also something that I hadn't really thought about, but which ended up working rather well. The simulation has a really good compromise in terms of spatial resolution and size box to study the transmission, the Lyman alpha transmission during the epoch of reionization. Okay, so which is why we have these two papers here from Max Gronke and from Hyundai Park upcoming. So this is already on arXiv. Okay, the Gronke et al. is accepted, and the Hyundai Park's paper is still in evaluation. It's also useful for extracting subgrid models for 21 centimeter predictions, as was done in the Gillet et al. 2021. So it's good to see that such a simulation, although it takes up a lot of resources to produce, ends up being very useful in different areas of the study of the epoch of reionization. So for Cosmic Dawn 3, so I plotted here, this is a plot I took from the Illustris website, where you see essentially the resolution in Y against the volume in X, okay, plotted with a number of well-known simulations. So CODA 2 is somewhere here, and Cosmic Dawn 3 pushes the resolution by a factor 2 in spatial resolution, a factor 8 in mass resolution. Okay, this required to go to a new supercomputer, which is Summit, the replacement of Titan, and to be allowed to run such a big simulation. Okay, so the grid is larger than what we had before. It's an 8,000 cube grid, so it required to run on more than 130,000 CPUs. So that's de facto the largest Ramses simulation ever made. All these CPUs were coupled to about 24,000 GPUs. The box size about 94 megaparsec, and with this grid, it allows us to go down to halo masses of about 2 times 10 to the 7 solar masses. Okay, and it ran down to redshift 4.7. It's important to run a little bit after reionization to be able to sample and describe a little bit what happens there. And since reionization nowadays ends up a little bit later than it used to, okay, because for some time it was redshift 6, now we're more talking about redshift of 5.5, 5.3. Well, you also need to run the simulations a little bit later than we used to. So in full, it took 10 days runtime on Summit. Okay, but it wasn't 10 days next to each other. These 10 days were spread about a period of about 2 months, in which you have bugs coming up, you have things crashing, you have all sorts of possible trouble that you have to fix in order to actually get the simulation done. And it produced about 20 petabytes of data, so that's a lot of data. So that's a fancy picture of the Summit supercomputer. And this is a short movie of what happens in the simulation. So here in blue, it's a small subregion of the simulation. In blue, you have the photon density. Okay, so I hope you can see these blue butterflies or blue bubbles expanding and also blinking because of stochastic uncontinuous star formation, I should say. Okay, on top of it, you see also the gas density. Okay, so you see the filamentary structure of the universe that we're used to. You see some red bubbles which start to appear, or at least which become visible in places where strong supernova feedback takes place. Yeah, and by the end of the simulation, the universe is full of photons. You're fully reionized. Okay. All right, so something which Cosmic Dawn 3 does much better than Cosmic Dawn 2 is reproducing the Lyman alpha opacities just after the epoch of ionization. Okay, here the dots are the observations. Okay, so Lyman alpha opacities measured in the line of sight of quasars. Okay, so Cosmic Dawn 2 would give something like that, the red track, whereas Cosmic Dawn 3 gives more something like the blue shades. Okay, so and we think the secret is in having this drop in the cosmic emissivity. Okay, and this drop is due to the combination of two things. You have a low mass population of halos which has a high escape fraction and which drives ionization for most of the time until ionization. Then it's radiatively suppressed, so its global emissivity comes down, and in the meantime you have a high mass population of halos which is trying to compensate for that, but which doesn't manage because its escape fraction is too low. Okay.
Yeah, you have 3 minutes left.
Ooh, okay, so I'll quickly go now onto the technical aspects, the things that could have killed the simulation. Okay, there are some aspects in the kinetic supernova feedback which we used, which were taking really a lot of time and which were a big bottleneck. Essentially, it had to do with finding where the cells impacted by supernova lived. Okay, so here there was an optimization which was done by turning a linear search along the space filling curve into a binary search, which is much more efficient. Okay, that was used, that really helped Cosmic Dawn 1. Cosmic Dawn 1 would not have worked without that, and that optimization was kept in Cosmic Dawn 2 and 3. Okay, maybe there's a little bit too much there than I can say, I guess, but I can come back to it if you need to. Some of the biggest problems I've had were with memory. Okay, so maybe you need to know that the memory usage displayed by Ramses can be very wrong, because the memory usage is collected via a system command, which is this one, and there's many values returned when you use this command, and formats may depend on the system. So in the beginning, I wasn't understanding what was going wrong with my simulation and why it crashed. And actually, I found out by looking at it more closely that the memory usage was wrongly displayed. Okay, so that's something to check for everybody who's having out of memory problems. The other big problem is that there's a huge overhead, which is due to the communicator structure. Okay, that's actually a known problem which was solved by Philippe Vautelet. However, the code resulting from this solution is I mean, there's a huge impact of these changes throughout the code, and it's not part of the main trunk currently, which is a bit sad. But actually porting these changes to the main trunk is a huge undertaking. It would be great to do that, but I don't know if we have the manpower of the will, the motivation to do that. I think it's really important, because if you want to do really high parallelism, it's kind of necessary to do that. Okay, in terms of IOs, so I hadn't had the chance to use the Hercules routine or library. in principle, on Summit, they have something which is called the burst buffer, which means every node has an SSD. And this SSD, in principle, you can write your data to the SSD, and then it's copied to the system-wide file system asynchronously. So in principle, your IOs are super fast, but there's a number of things which prevented it from working properly. For instance, a competition between the CUDA MPS and the burst buffer daemon, which we're trying to run on the same core. So even though I talked with the system admins about that, we weren't able to fix it together. So I had to live with the usual Ramses IOs, which means you have to be nice with the file system. And so I used the parameters which are given here. Okay. And also for startup, I don't know why, but starting from one single initial condition file, when it's very large like that, 8,000 cube, it just didn't work out. I don't know why. So I had to use split graphic so that every core has its own initial condition file. It was very slow if you use the version which is in the main trunk at the moment, but you can actually accelerate it by a very significant amount when you have equal volumes as computational subdomains as we have here. Okay, so, oh, sorry, that's my conclusion here. Okay, so I presented you the cosmic dawn simulations, and in particular cosmic dawn 3. They are the biggest, largest radiation hydrodynamics simulations of the epoch of reionization ever made. Getting them to work was not a walk in the park. Okay, it's really hard, as you can judge by the number of bottlenecks and bugs that I had to fix and deal with in the meantime. So CUDA 2, Cosmic Dawn 2 worked already pretty well, but Cosmic Dawn 3 works better, in particular thanks to the mechanism that I explained, where suppression plays an important role in preventing the Lyman alpha forest from becoming too transparent after reionization. Okay, and yeah, so I think I'll stop here and just say stay tuned for the Joe Lewis's talk, where he will present more science results from this simulation. Okay, that's it. Thank you.
Thank you, Pierre. Do we have questions? Johan, yes. Oh, you are mute, Johan.
Sorry. Yeah, Pierre, wouldn't you have a huge benefit of using an OMP version of Ramses, especially for the overhead you mentioned?
I wonder if the OMP version actually addresses this overhead or not.
Well, you have fewer MPI processes.
If there are fewer MPI processes, then yes, you are right. Yeah. This would probably go a long way towards fixing that. Yeah.
Right. If you have 64 cores per node, you can divide by 64 the number of MPIs. Right?
Yes, that's correct. Yeah, good point.
Any other question? Well, Yuki, yes.
Hi Pierre, thanks for the talk. Can you remind us these file output parameters, IO group?
Oh yes,
that other one.
Yeah.
What do they do?
Oh yeah. Okay. So the first one, IO group size, is to prevent all the files, all the processors from writing all at the time to the file system. Okay, because if you have 100,000 processors trying to access the RAID and trying to write on the RAID, things go wrong. So here, this allows you to have them take turns. I think this means, if I remember right, that there's only here 131,072 divided by 32 processors which are allowed to write at the same time and read at the same time. And then the next parameter means that you're not putting all your output, all your files in the same output directory, but that you have subdirectories, you know, like output 1 _1, output 1 _2, etc., so that you don't have too many files in the output directory. Okay, So this will mean that each subdirectory of output will have 8,000 processors writing in it. Was that clear?
Yeah, totally. But you still get I guess about 1 million files per output then, right?
Yes. So this is to prevent exactly that. It's to prevent having 1 million files in each output directory. So each thanks to the subdirectories, you have something more like 80,000 files per subdirectory. So it's much more manageable for the file system. You actually get you get crashes because of that. It's not just that you can do an ls in your directory afterwards. It's really you're going to crash.
So how do you store 20 petabytes? Did you say that of data?
Yeah. Well, at the moment it's still at the moment and even in the short term, and yeah, it will stay at the facility in the US. Okay, we can't bring that back. So we are processing at the facility there. So we're using more summit hours in order to do, for instance, the FOF halo finding. Okay, so that's done there, and also the first attempts at what Joe will show you this afternoon. He's also doing that already. I mean, at the facility in the US. Okay, and there's a smaller cluster which is still quite significant. It has more than 500 nodes, which is there, which is accessible to analyze the simulation. So the hardware is there in order to analyze the simulation without bringing it back to Strasbourg.
Thank you.
Okay, thank you. Thank you to all speakers of this morning.